Thank you, everybody, for joining us for C2 Smarter's third Women in Transportation series installment. Today, we are joined by Ilgin Guler, who is an associate professor in the Department of Civil and Environmental Engineering at Pennsylvania State University. Her research interests include multimodal urban traffic operations and control, intelligent transportation systems, connected and autonomous vehicles, and infrastructure management. She will be presenting her seminar titled Location Selection and Investment Sequencing for Transit Priority. And a reminder that this seminar will be recorded and uploaded to YouTube. And please ask any questions throughout the seminar. You can do so by pressing the Q&A button, and then we can read them out at the end of Professor Guler's presentation. And with that, I'll hand it over to her.
Thank you for the introduction, Lizzie. Is my mic good? Anybody can confirm? Assume so. Okay, sounds good. Well, thank you for being here today, and good afternoon. It's my pleasure to join. And so just before I get started, I want to acknowledge my PhD student, Murat Bayrak, who's currently a postdoc at Aalto University, who did a lot of this work. And before I jump into the work, I want to give you a little bit of background on myself, on the work that I do, because this is just kind of a portion of my research. So I like to think of myself working in this managing transportation infrastructure space. And I have a variety of different topics that I'm interested in: multimodal traffic interactions, traffic management and control, public transportation, traffic safety, infrastructure management. So in the multimodal traffic interactions, this is a lot of my PhD work that I did back in the day. I looked at how can we use existing road space in a more efficient manner for people travel, so to get more people through the roads, which implies we want to kind of give buses some priority, but we also don't want this bus priority to lead to too much congestion for the cars. So I've looked at different kinds of approaches to dedicated lanes or signal priority that can be used to achieve that goal. In the traffic management and control side, I've done a lot of work on signal control, specifically using connected vehicle data. So I'm not an autonomous car person necessarily, but I assume connected vehicles exist and then see, okay, what can we do at the signal level better to manage the traffic operations. And then I am recently doing some more work on traffic flow prediction. How can we use more machine learning, artificial intelligence types models to do better prediction of traffic flow, especially on highways. In the public transportation space, this is kind of where today's topic lies in. How can we determine where do we want to prioritize buses? Where do we want to implement dedicated lanes or transit signal priority? How can we make those decisions at this aggregate level? In terms of traffic safety, the theme of multimodal kind of continues into there. I look at multimodal safety, so I try to use data to understand pedestrian and bicyclist safety, and how we can better understand what factors lead to pedestrian and bicycle crashes. And then, sorry, I went backwards instead of forwards there. So, and then finally, infrastructure management. This one might seem kind of out of left field, but a lot of what I do in infrastructure management field is data analysis and optimization. So I do a lot of work on predicting the future condition of our infrastructure using data, or trying to determine how we can make better decisions for maintenance and repair so that we can use the budget that's available for infrastructure management in a more efficient manner. So how can we kind of improve the quality of the infrastructure while spending the same amount of money by making smarter decisions? So with that in mind, I'll jump into today's topic. I'm, again, in that more public transportation, multimodal space today. So we all know congestion, large issue, right? You have a whole center on trying to manage congestion. And the two ways of dealing with congestion, as you know, is you're either trying to manage demand because you can actually try to change how we use these facilities that we have existing, or you can try to address the issue of capacity. How can you improve the capacity of the roadways? So the way I look at it is from a public transportation perspective, which is trying to kind of use the available capacity in a more smart manner, and hopefully kind of changing what the demand looks like, especially for cars, through this smart management of the infrastructure. So I focus on public transportation, and you can imagine that especially in large urban areas like here, you have some infrastructure that can be dedicated to the multimodal modes such as subways and trams. You can put them underground, don't let them take up space on the roadways. But even so, you still rely on buses quite a lot for public transportation, even with the existing of the subway system. And buses are trickier, right? Because buses, you can't kind of take them and put them on their own facilities easily. You have to use the existing roadway. The existing roadway is limited. There's buildings all around. The width is limited. So you're trying to figure out, how can I use this road that I have and give priority to these buses? So what I'm trying to do is try to make bus transit more efficient and reliable using transit priority strategies. Seems simple enough. But the problem is, again, in, for example, Manhattan or here, Brooklyn, you're going to have issues if you take away a lane that is for cars and say, okay, only buses can use this. And if there aren't enough buses, then you're wasting that whole space and you're not moving enough people to make up for the congestion that you're adding to the cars. So there is a fine balance of, I want to prioritize the buses, but I also want to make sure that when I prioritize the buses, that makes my whole system more efficient. So I'm not just prioritizing buses and maybe moving the 30 people on the bus every 2 minutes through this corridor while adding 10 minutes of delay to the other 100 cars that are waiting in line trying to get to the same intersection. So what I really try to do is try to account for, how does this priority impact the entire system? How could it lead to mode shift? And how can we better manage a network-wide signal priority considering all of these impacts? So the research goals are to develop a bimodal kind of bi-level strategy, and where we have a lower level model that is capable of accounting for the impacts of Q spillover. So that one is critical. This accounting for Q spillover is actually a hard problem because that means the dynamics of the roadway are very different than perhaps potentially linear models that might be used to account for traffic in typical models. So we have dynamic impacts of Q spillovers. We're trying to account for dynamic route choices. So if a road is congested, people try to reroute themselves. We have a dynamic mode choice model as well. So when kind of things settle in, some people might say, oh, bus is a quicker way to travel for me, so they might switch to the bus as well. And we're trying to do this all in a computationally efficient manner, which is complicated. And then we're trying to optimize this transit signal priority on a network, which I'll explain in a second. And we're trying to figure out what kind of an optimization algorithm should we use so that we can, again, run this whole process and be able to solve and find a good solution. This is the overview of what I'm going to talk about. And today, I'm not going to look too much at this lower level. I'll kind of give you a flavor of how I do the evaluation of these transit signal priorities and how they impact delays overall. But I'm really going to focus on the upper level and I'm going to focus on this optimization strategy. But the whole idea is we have a network. On this network, we're trying to implement transit priority. Transit priority, I'm keeping it kind of vague at this point because I've done this for multiple different strategies. I've done it for dedicated lanes. I've done it for transit signal priority. So it could be the transit priority, could be different things here. But you have a set of locations on a network where you want to put transit priority. You evaluate how that priority impacts travel time using a lower level model. So this lower level model estimates travel times through a link transmission model, does a mode choice, does a route choice, and kind of runs this until we have settled on a mode choice and a route choice that kind of works out. And then we get a total travel time for that specific set of priority locations. And then we try to figure out at the upper level which one of the locations that we're interested in is the best location, which is our optimization step. So again, this upper level is kind of what I'm focused on today. But before I focus too much on the upper level, let me give you a flavor of what's going on at the lower level. This is, again, the model that evaluates and spits out total travel time for me to use as a metric, basically. My goal is to minimize this total travel time that is for the cars and the buses. So my lower level is a link transmission model. I have a network. The network consists of nodes and links. On top of that, I assume I know some kind of jam density capacity, which is an input to the link transmission model. The nice part about the link transmission model is that it is an analytical model. So you don't have to, there's no randomness in it. So every single time you run it, you get the same answer. So once you have your network configuration and everything in place, you can get a total travel time, and it's not like a micro simulation where you have to run it multiple times to make sure you're getting rid of the randomness. And then I have a bus network configuration that goes into that. I assume there are bus routes on certain links that the buses travel through, and then I assume I have a fixed set of locations for my transit priority. And I also assume that I know the demand between origin and destinations, but I assume I know the demand in terms of people, not in terms of vehicles. So I assume I know 10 people want to go from location A to B, not 10 cars. So how those 10 people go from A to B, it could be car or bus. I let them kind of figure that out using the mode choice model. So this is what the link transmission model looks like. You give all those inputs. You have a network. And if you're familiar with traffic flow theory, it is a kinematic wave theory-based model. If you're not familiar with traffic flow theory, it basically just assumes a fundamental diagram and propagates cars from link 1 to link 2 based on congestion levels, available capacity, and how much road space is available. So it obeys kinematic wave theory, and that's what makes it an analytical model, not a microsimulation. And then you do this in kind of discrete time steps. If you're familiar with a cell transmission model, it's like one level more aggregate than a cell transmission model. But if you don't know any of that, all you need to know is it's an analytical model that can propagate cars from links so that you can run through a certain duration of time and figure out the total time it takes for cars to move in this network. Is there any questions about that part before we move on? Okay. And then the link transmission model is fairly commonly used, I guess. But we've added some additional models to it to be able to tackle this problem. So we have the route choice and the mode choice models. we assume a logit model for these, and we assume demand gets distributed among alternative routes based on the travel times that the link transmission model predicts, and that we have the route choice, the mode choice, again, similarly, where people choose between a car and a bus, and we assume that we run a simulation long enough that the route and the mode choice stabilize towards the end of it. We also have a bus tracking algorithm that's added to it. Because buses are less frequent, we kind of track them one by one along this. So we say, okay, bus 1 enters link 1 at this time. We get the travel time on that link. So we say, okay, bus 1 must exit this link at this time, and we kind of track buses individually. And then using these models, we calculate the car travel time, and we calculate the bus travel time as well. So that we end up with that total, what I call the total travel time on the network of car and bus users. And so we do that total travel time calculation for the last 30 minutes of the simulation, where again, I assume that mode choice and the route choice have stabilized. Okay, so what I really want to focus on today is how do we optimize this transit priority locations? And I'm going to show 4 different algorithms. And before I show the 4 different algorithms, I want to talk about why is this a challenging problem? What is unique about this optimization problem in the context of transportation and queue spillovers, to kind of justify why I will show those 4 algorithms and why I think we need to try these ones, and to kind of, again, justify the final choice of the one that I think works the best in this specific context. So the test network that I'm going to show today is a 4x4 grid. Very small, very simple. It's very small and very simple for a specific reason. I need to be able to enumerate all solutions here to be able to demonstrate the effectiveness of the optimization algorithm. So I start with something that I know the solution to, so that we can actually find the algorithms, the heuristic algorithms that can get to the actual solution. So that's why it's like a small, simple network. And in this network, I assume I have 2 bus routes, one that runs up and down the middle here, and then one that runs right to left in the middle here. And I am going to try bus lanes for this demonstration. So I'm going to assume that each direction can get its own bus lane. So I might have a bus lane in this link 1 going up, or I might not. So each number here, 1, 2, 3, 4, is a candidate to getting a dedicated bus lane. A dedicated bus lane in this case, I assume I have 2-lane roadways. So I take 1 lane, say only buses can use this lane, and I keep the other lane for cars. Or not. So I have 16 potential locations. That ends up with 65,536 potential combinations of bus lanes that I can put on the small network. And I'm trying to figure out what is the best combination to minimize my total travel time in terms of person delay. So car plus bus delay when I convert it to people delay. That's what I'm going for. So the first step is I want to show why does this need its own algorithm? Why do I even need to kind of go into the optimization algorithm? Why am I not just using any heuristic out here? So the problem with this optimization is that there is a dependency on the solution set, meaning each link is not independent. So if you put a bus lane on 1 link, whether you put that bus lane there or not changes the entire landscape of the solutions. I have a large chart here. I'll explain one in detail. But each one of these is link 1, link 2, link 3. So each one is a candidate bus lane location. And the distributions are the distributions of the change in total travel time between having a bus lane on link 1 and not having a bus lane on link 1 for different combinations of bus lanes. I know that's complicated. Let me explain. So let's focus on link 1. Link 1 is this one here, going up this way. So what we do is we say, okay, I'm trying to understand how does link 1 impact the total travel time. So if I add a bus lane on link 1, does it always decrease travel time? Does it always increase travel time? What does it do? So what we do is we say, okay, let me look at a combination. Let's say this is my set of bus lanes. And then I put bus lanes here. I calculate the travel time. And making up numbers here, let's say it's 100. So this would be, for this configuration, total travel time without link 1 having a bus lane. And then I do the same thing, and I add link 1. So say now I have a bus lane on link 1 as well. And let's say when I do this configuration, again, I evaluate it. I get the total travel time, and it's 98. So then I say, OK, in this case, link 1 reduced my total travel time by 2%. So that would be kind of one red dot on this left-hand side. So that would be one count for the minus 2%. And then I do it for all the other combinations. So then I try another combination. Say I had bus lanes on all of these links, and I had a total travel time without having a bus lane here. Let's say, again, it was 100, again, making up numbers. And then I add link 1. I evaluate the total travel time again. And then let's say, in this case, adding a bus lane on link 1 increased the travel time. So now I have the percent change is 1%. And so that one becomes a red count over on this 1%. You might ask, why would adding a dedicated bus lane increase travel time? Well, you probably increase congestion, right? So if you added a dedicated bus lane, there wasn't enough priority to the buses, reduction in bus travel time to offset the increase in congestion. So not every bus lane is great in this context. So basically, we do this for all the combinations with and without. So that means I have 2 to the 15 different combinations that I evaluate with link 1 and without link 1, and I plot this percent change in there. Okay, so having gone through that exercise, let's go back to this full figure. So this full figure is, yes?
How sensitive are those percent changes to your demand patterns?
So that's a really good question. We haven't, this is for uniform demand. And of course, they would be sensitive. So it wouldn't look the same if I had a different demand pattern. And the whole exercise is not necessarily to say link 1 is good, link 7 is bad, but it's to show that different links have different distributions. And you would expect that to happen with different ODs as well. So what we end up finding is that, first of all, for all links, they're sometimes good, they're sometimes bad. They sometimes increase congestion, they sometimes decrease congestion. But we find that some of them, like link 8, link 12, have much narrower solutions. So their ranges of change are much tighter as compared to some other ones. For example, link number 6 sometimes does really well, but oftentimes does bad because it's skewed towards the positive side, meaning it's increasing travel time. And interestingly enough, the red ones that I'm showing are the ones that we find are to be the optimum set of links in the final solution of the enumeration. So what we end up finding is that typically if a link doesn't have a large variation in terms of how it would change travel times, that link ends up showing up as in the optimum solution. So there is this issue of dependency and linkage between the links that an optimization algorithm needs to be able to account for, or should account for more efficient solutions. So in this case, I was able to enumerate the solution. But again, if I have a larger network, I will not be able to enumerate the solution. So I need to rely on a heuristic. And the heuristic that I choose, if it can somehow use this property of dependency, it might be able to get to a better solution or be able to get to the solution in a faster manner. So with that kind of understanding of the solution space that we're looking at, we tried different upper level algorithms. And the first one, basic genetic algorithm, we tested that one. We don't expect it to do well, but that's kind of what's used in this field typically. When you're dealing with a location selection problem in the transportation network field, oftentimes the solution algorithm is this basic genetic algorithm. So then we tried, okay, let's modify that genetic algorithm a little bit. So we have what we call genetic algorithm with diversity management. I'll go over all of these in a little bit more detail. Then we tried a Bayesian optimization algorithm to try to really get to those dependencies. And then we tried one last one, the population-based incremental learning. Again, these last two we specifically targeted to try to deal with that dependency problem. Yes? Yes. It's typically the exterior links that perform better because interior links add too much congestion, at least in our scenarios. And again, because it depends on the demand pattern that we're dealing with, I don't want to generalize a statement. But in these uniform demand patterns that we deal with, we find that these links are on the outside of the network because the inside ones just add too much congestion to the network. And I'll get into that in a little bit again towards the end as well.
One more question. What exactly this point you're doing here? You mentioned that you're selecting different points, not the I don't know if I understand it clearly, but I think you are selecting different lanes and points.
I'm selecting lanes in this case. I'm doing dedicated bus lanes on links. Yeah. So I'm trying to find the links where I want to put these. So it's in between two signalized intersections or two intersections. Any other questions? Yes?
You go to you show the arrows?
Yeah.
So in that case, I imagine because there's two bus lines which are not connected,
Yeah.
so, a lot of line changes and that question. Is that taken care of in the lower?
That's taken care of in the lower level algorithm, correct? Yes. So yeah, so if this one, for example, would mean that there's two lanes coming here, they need to merge into one. So yes, that would lead to congestion on this link, correct? Mm-hmm. Any other questions? Okay. So then looking at the solution algorithms, genetic algorithm, I'm assuming we are all familiar with this. I'm not gonna go through it, but it's typical, you have parents and then you produce offsprings and you go through multiple generations and you find the best chromosome. And a chromosome in this case is, we have, for example, if I had 8 potential candidates for bus lanes, a solution would be whether 1 or 0, whether or not there's a bus lane on that link. So if I had bus lanes on links 1, 2, 5, and 6, I'd have 1, 1, 0, 0 for 3 and 4, no bus lanes, 1, 1, bus lanes on 5 and 6, and then 0, 0 again for 7, 8. So that's the chromosome structure I'm looking at, 1s or 0s for each link. And that kind of stays consistent throughout the solution algorithms. For this one, we do try to add a little bit of management for the diversity of this one. And the parent selection is where we kind of focus at. We use the tournament selection procedure so that we can, and I'm not going to go into the details of it, but we're trying to basically balance out the solution state so that we're not stuck in kind of one solution or one non-optimum solution space. Then what we find is that when we do this, there still isn't a lot of diversity. So skipping through some of that details there, but what we end up finding is that in the solution space, we still don't have enough diversity. We're still kind of, once we find something that works a little bit, we get stuck in, for example, if we find that a middle link works well, we keep finding that that middle link is always showing in the solution space, we can't kind of diversify. So we add external diversity steps to see, okay, maybe it's just an issue of we're not exploring the whole space. Let's try to figure out if we can explore the whole space, if the genetic algorithm can do better. So we add diversity management steps at each generation. And if it's not sufficiently diverse, which we measure with a diversity metric, or the best solution has not improved in 10 generations, we kind of get rid of half of our solution and create a new random generation solution to try to, again, increase that diversity. So the whole idea is let's not get stuck in one suboptimal solution. The Bayesian optimization algorithm, we fit a Bayesian network to our solution space so that we can evolve it using the Bayesian optimization. So we have a Bayesian network that's fitted to our solution space, and we sample from that for our solution. So this one, because we create this Bayesian network of the solution space, it doesn't have that inherent assumption that each chromosome is independent of each other. We can actually try to capture some of that dependency by creating this Bayesian network. And the initial steps are fairly similar, where we have an initial population and solution step, but then once we pick our parents, we have this separate Bayesian network optimization algorithm, where we have a Bayesian network, we have no edges, we add edges, and these have nothing to do with the actual physical network. They have to do with how a bus lane on each link might depend on the existing of other ones. So we might say, okay, the bus lane on 1 is highly dependent on what's going on 2. So if you have a bus lane on 2, the impact of adding also on 1 is going to be much more different than, say, if you had a bus lane existing on 5. So we try to create this Bayesian network of the solutions and fit these edges in a separate optimization algorithm. And we deal with the Bayesian information criteria to try to fit this network at each step. And then using this dependency structure, we try to create new solutions. So again, the whole idea is, can we use the fact that there are dependencies that we showed through the multiple 16 4x4 figure and exploit that? And then we create those new solutions. So that one is, in theory, a good approach. The problem is it is very computationally expensive because you are fitting a Bayesian network at each step. So it's kind of computationally intense to be able to do that at each step. So the last one we try is this population-based incremental learning. It is very similar to a genetic algorithm, and I don't know if you're familiar with it, But it kind of combines the generational evolution of genetic algorithms with a competitive learning. And it has a probability vector that it keeps track of rather than a fitness score that a genetic algorithm keeps track of. So just to start with an example, let's say we have 6 candidate locations for bus lanes, A, B, C, D, E, F. So I could put a bus lane on link A or not, on link B or not, etc. So it kind of starts off with not a 1-0 chromosome. Yes, there is a bus lane. No, there isn't a bus lane. But instead of that, it has the probability. There's 50% chance that I will put a bus lane on link A. So it starts out with 50% chance for there being a bus lane on any of these locations. Kind of, we have no idea. And then it creates an initial population based on this probability vector. So once we know the probability vector, then it kind of randomly samples, okay, I'd create a random number greater than 0.51, smaller than 0.50. So each one of these rows created with a random number generator based on the probability thresholds. And then it evaluates these ones, puts them into the lower level algorithm, gets the total travel time, figures out, okay, this one led to the smallest travel time, this one led to the largest travel time, and then based on some math, positive learning, negative learning mutations, it creates a new probability vector. So now, for example, maybe A, having a bus lane was bad, not having a bus lane was good. So it said, okay, maybe I should reduce the probability of putting a bus lane on link A based on these equations. For maybe B, it was good, also bad, but maybe I'm going to increase the probability. So based on whether or not it's in the good solution or not, it changes, updates that probability vector, and then kind of repeats that process and creates a new population, evaluates, creates a new population, evaluates, creates a new population, evaluates, and the final solution is simply any one of these that has greater than 0.5, we say is in the final solution. So in this case, my final solution would be 0, 1, 0, 0, 1, 0. So I'd kind of base my final solution on the prefixed threshold of probability. So I don't really pick this one. If it was the best evaluation, that's not necessarily my solution. Okay, so for testing this one, we looked at a slightly larger network. We have this 6x6 network, 4 bus routes, actually 8 bus routes, 1 in each direction. All the other parameters we used are in here. I'll kind of skip over those and show you the solutions. So first of all, we evaluated no bus lane anywhere, bus lane everywhere. What does the solution look like? As expected, bus travel time decreases when you put the bus lanes. Car travel time decreased as well. I'll get to that in a second. And the total travel time increased. So actually, having bus lanes everywhere is better than not having them anywhere for this test network. Again, don't generalize my conclusions, just for this test network and this demand pattern. The reason why it's better is that, well, when the bus travel time decreased, people switched to the bus. So more people are using the bus mode share became 36%, which explains why the car travel time decreased, because less people were using the car mode despite there being less capacity available for those cars. Overall, it was better for them. And this one is how the different heuristics performed for this test network. So we ran each of these algorithms 30 times. So we ran the genetic algorithm 1 30 times, genetic algorithm 2 30 times, etc. And this histogram shows what the best solution of each run of the heuristic was. So blues are GA1s that are, you can see they're mostly towards the right. So most of the runs of GA1 were fairly on the higher end of travel times. Reds are GA2. Again, most of them are here. You can see the yellow and the purple are more focused on the left, meaning they performed better oftentimes than the GA1 and GA2, and the best solutions came from the purple and the yellow. And you can kind of see this table shows the total travel time. So 1919 and 1817 was no bus lane, full bus lane. You can see with the optimization, total travel times are much lower than 1817. So the optimization does actually improve, means it finds a better solution than what kind of the standard solutions. And this shows the range, minimum, average, and maximum. You can see the average of the PBIL was actually the best, 1593. The minimum was the best, and the maximum was the best. So PBIL and BOA kind of perform similar, with PBIL slightly edging it out. Part of the problem is that the BOA, again, is computationally expensive. So actually, if we evaluated, and sorry, I forgot to mention that we evaluated the same number of solutions for all of these. So the limitation was we're going to evaluate the same number of solutions for all of these to figure out which one can get the best. So for the BOA, we evaluated the same number of solutions, but because we had to fit the Bayesian network in each one, it actually probably wasn't enough number of solutions. So for the same computational efforts, the PBIL performed the best, if that makes sense. And then we looked into it a little bit more. So this goes back to your question about where are these bus lanes typically. So the green ones show where there were bus lanes. The red ones show where there were no bus lanes. And this is the first best configuration, second best configuration, third best configuration. You can see it's almost always on the outer links. And this is the breakdown of bus and car travel time for each. You can see that actually these solutions have even lower bus travel times than a full bus lane, which is kind of interesting. Is an interesting solution to get that even for the buses you can actually do better. Okay. And then this is the distribution of common bus. Oh, did you have a question? Sorry.
Is there some basic intuition as to why having more bus routes would not be better for the buses themselves? I understand why the system might not benefit, but why would the bus itself not benefit?
Yeah, so I believe what ends up happening is that when you have a full bus lane, there is issues at the intersections where the bus lanes coincide with the buses kind of getting stuck amongst each other. So when you don't have the bus lanes everywhere, you kind of get the same level of priority, but then the buses don't arrive at the intersections necessarily at the same times. Because here, for example, you have the bus lane. Let's look at this one. You have the bus lane going out of here, but when you have the bus lane all the way through, the way, it might be a kind of an artifact of the algorithm as well, but the buses kind of arrive, because this link is free, they arrive at the intersection at the same time. So they kind of experience the full red time in that case, as opposed to when they actually go with traffic, they don't experience the full red time, which leads to less delay. It is an interesting artifact. I think it has something to do with perhaps an artifact of this again. Yeah, I'm not 100% sure that it would happen in reality, but it does. What we end up seeing is kind of they don't come at the same time. So one bus doesn't experience the full delay at the red light. And then this is kind of the common locations found in the best solution for those algorithms. The interesting thing to note here is that in genetic algorithm, in its best solution, sometimes chooses to put bus lanes on the insides, whereas for these two, in their best solutions, the inside is always omitted. So in the no solution, does the inside show up as being the best location, which again goes to show that it can kind of eliminate some of those dependency problems better with those algorithms. We looked at the exploration capability. So again, I said we evaluated the fixed number of solutions. That was our criteria. And we looked at number of unique evaluations, meaning how many of those fixed number of solutions was unique. It wasn't repeated. And we found that the PBIL did get to the most number of unique evaluations, which again probably helped it find the better solution, whereas the GA, the genetic algorithms, were kind of stuck in one area despite diversity management. And then the generation number in which the final optimum solution first appeared, you can see that the minimum is, 9 was, went up to 100. 9 was, you shouldn't be able to find your optimum solution at the 9th generation for such a complex problem. You can see kind of, again, these ones were able to explore the whole space of solutions a little bit better compared to the genetic algorithms. So all of these kind of led to us saying that these two algorithms, for specifically this location selection problems or these types of problems where there's dependency, are likely to outperform the genetic algorithms. So just to wrap up here, and then I can take some more questions. The genetic algorithm, which is typically used for these types of problems, might not be the best, especially if there's this linkage dependency problem. And then the Bayesian optimization and PBIL, population-based incremental learning, is probably a better algorithm to use for these types of problems. That's all I have today. Thank you for your attention, and I'm happy to answer any questions.
We have one online question, if you guys can hear me.
Mm-hmm.
This is from Professor Chow, who says, he has one question and two comments. So the question is, why was a metric of total travel time used if the mode choice is a logit model? Could you have evaluated based on expected utility or some log sum value?
Okay, that's an interesting question. I'm trying to actually think about how we would have evaluated based on the expected utility.
He has a follow-up comment if that.
Yeah.
He says, bus lanes seem to work better as paths of bus lanes as opposed to evaluating them as single links at a time. Did you consider solutions based on paths of bus lanes?
Yes, okay. So I can answer the second question quicker than the first one. The second one, yes, we did. Actually, when we first tackled this problem, we tackled it in a way where we broke down the network into quarters and only dealt with the quarters. So we dealt with a larger network, but we only looked at kind of a quarter and looked at bus paths existing in these quarters. And we ended up finding that actually the bus paths were not always the best solutions, especially because you end up finding that sometimes you don't want the full, for example, link to be a bus lane. It also depends on if you're dealing with sending links versus receiving links. So oftentimes sending links, we ended up finding that you want just little portions of bus lanes versus receiving links. You oftentimes wanted more bus lanes because they led to less congestion. So yes, we did evaluate bus paths, but it wasn't always obvious what that a bus route on a bus path would be more efficient than individual links. So I can answer that one. The first one, I'm still trying to digest your question. So the travel time was our metric because overall our goal is to improve the system. And when we are trying to improve the system, what we really, really want is that people on this network travel at the smallest travel time. And so actually when I talk about total bus travel time, I'm not actually talking about the buses themselves. I'm talking about the people who use the buses. And when I'm talking about car travel time, I'm talking about the people who use the cars. So because I was really considering the people's experience, we wanted to focus on that as our metric as opposed to anything else. I don't know if that answers exactly the question.
And then he has one more comment, which is just that he's also surprised that the mutation rate is not already controlling for the diversity. The multi-objective GA algorithms have introduced diversity metrics that can be used for evaluating fit of solutions relative to others in the population.
Okay, so the mutation rate, we've played with the mutation rates for the classic genetic algorithm. It doesn't get you far enough, unfortunately. The algorithm kind of keeps getting stuck back in its original solutions. We've played around quite a lot with the mutations. I'll get back to this question in a second, but for the multi-objective genetic algorithms, I'm actually not familiar with those. So if you don't mind sending me maybe a reference paper, I'd be interested to see how that might compare to the PBIL.
And then one last comment is, which I think is a follow-up to your answer previously, but he said that people's choices of modes and routes are not just deterministically based only on travel time, they are utility functions. But he also says he can follow up over email.
Yeah, I definitely understand. And the one thing I will say about that is that we found that the solutions weren't sensitive to our utility function for the route choice or the mode choice too much. So I think even though the route choice and the mode choice were based on a utility function, I'm not sure that it changed the final evaluations of these kind of solutions.
Great, and that's our last, so far, our last Zoom question, so feel free to take any more in the room, otherwise we can wrap up.
I can start over back there. Yeah.
I remember in your slide 16, you mentioned the lower the variance of those the changes stuff, the higher possibility that link will appear in your final solution. But what happened to the upper right?
Yep, that one did not show up in the optimal solution, and we were not sure why. It's a very good question. You're talking about this one up here, right? Yeah, this one also has a very narrow range. And we tried to understand why that one might not be showing up, but I mean, this is an enumeration, so it just, for some reason, did not show up in the solutions. We weren't sure why either. Yeah.
Second question is, I thought I missed part of your explanation. So I think in your slide 27, you show multiple files with different algorithms, and you show that for certain algorithms, their distributions are more redshifted or left-shifted. So first, I didn't understand where this stochasticity come from. Do you use different initialization?
Yes. Okay. Yeah, they start with different random seeds. Yeah.
So if that, what's the motivation of this approach? Is it because they're naturally sensitive to some initial conditions? Well,
yeah, so it's a very good question. So it is kind of interesting that if you look at the range of solutions, the ranges are much tighter with these PBIL and the BOA. So they're actually a lot less sensitive to kind of where you start from or what your random seed is. But the genetic algorithms, because they don't explore or they get stuck in suboptimal solutions, their actually range is much larger. So that is an interesting point that for this type of a problem where you have this dependency on the solutions and your computation is kind of costly, the genetic algorithms, one solution is probably not reliable. So even if you are going to use a genetic algorithm, you probably don't want to just try one random seed because it gets stuck in suboptimal solutions. It is actually an interesting finding that the genetic algorithm doesn't always do, doesn't even result in the same solution.
My concern is that if the network even larger or even more complicated,
Yeah.
I think this phenomenon will be more
Yeah, absolutely. Absolutely, yep. Yeah, no, absolutely. That's kind of why, like, I think the optimization algorithm that you use is important to be able to get a better solution if you cannot run this thing like a million times. So in this case, like the actual accounting for congestion time is computationally expensive. So it's not feasible to run this for probably as many generations that it would take the genetic algorithm to get to the optimal solution or closer to the optimal solution. And so especially in these computationally expensive problems, it's important to pick the correct optimization algorithm. Yeah. Yes?
You mentioned something about solving problem in an efficient computational manner. My first question is how much this framework is efficient and whether it is possible to apply on a real world problem like a real network.
Yeah, so the link transmission model is the bottleneck here. The heuristics are fast, obviously, because they just kind of, once you have the lower level solution, the heuristics run fast. The lower level evaluation is computationally more expensive because it is keeping track of a lot of large matrices, basically, that take all these numbers in and try to kind of do calculations. So it's these kinds of networks, we have expanded this to about a 10 by 10, but that's kind of where the computational limit is, especially on like a regular computer. I mean, you can run these on supercomputers and of course you can like solve them, but it is limited by the computational efficiency of the link transmission model. But that one is kind of necessary to be able to account for Q spillbacks, because in a problem like this, Q spillbacks are huge because you put a bus lane in, there's a Q spillback, and the Q spillback is hard to track in a in an analytical manner. So microscopic simulations can do similar things, but then the problem with the microscopic simulation is the microscopic simulation itself is random. So you have to run the microscopic simulation itself multiple times. So in both ends, you kind of end up in a computational bind. So it's not the computational efficiency is not in the lower level algorithms, and it's hard to make that computationally efficient. That's why we're focusing on the upper level algorithm to see how you can use the same available like computational capabilities to get to a better solution.
So is one of the generalizing ways that the population-based reinforcement learning is going to be generally better than the genetic algorithm, almost always better, or is that just kind of subject to a lot of the specific instances of the problem?
Yeah, so we've tried it for this bus lane work. We've tried it for transit signal priority. A colleague of mine has tried it for like banning left turns. And for all instances, we've found that the PBIL performs better than the genetic algorithm. So I think it's safe to say that in many instances, it is going to outperform the genetic algorithm. Of course, I cannot say, right, that it's going to do in all, but I think because we kind of understand why it performs better than the genetic algorithms, especially with this linkage issue, I think it's I think it will oftentimes outperform, yes. Yep, thank you all.